email or?
Looks like
So, I don't hear it. All you have to do is just sit.
whenever I present it's a deal.
You have the pointer of authority. You have the pointer of authority. So if anyone falls asleep, just whack us.
Exactly.
Whack-a-mole.
There's some visions. You guys will do that.
There's probably just a cat here. You give it a few days. It'll go away.
Freak people out and walk down the aisle.
I always do like wild interpretive dances.
Normally it's
Wakes them up.
we can get the iPad and do the spectrometer. We can just spectrograms and see where it's going.
There is some sort of competition with dance and PhD.
Yes.
It wasn't around when I was there.
It was actually had just started when I was graduating, but I was like, I have no idea what I would do.
Well, one point trend is very much
Yeah.
What's going on with the rails?
So,
You do the cards.
She's 20.
I'll sit down. Sorry about this.
Okay, now that Dean has sat down, it's my pleasure to introduce Dr. Scott King. Scott is a professor in the Geosciences Department at Virginia Tech. He's an internal dynamicist, so he measures the evolution of the interior of solid planets. I met Scott through the Dawn mission at Ceres, where we were both guest investigators on the team. And Scott is now a participating scientist on the active Mars InSight mission. So if you have some time to catch him this evening or tomorrow, definitely bend his ear about InSight. It's a really exciting mission that's going on right now. And I'm very pleased to have Scott here today. And with that, welcome.
Thank you. Sorry, not a Patriots fan. Who that is, I don't know.
Sit back
Sorry. They need coffee, but we'll see. So, as Hannah said, I met Hannah through the Dawn mission, and it was the first time. I've spent most of my career working on Earth. Then I moved into Mars, and this was the first time that I'd actually been involved with a mission team. And as you know, Dawn went to Ceres. However, I realized NASA didn't need to send a spacecraft. Here's Ceres, Virginia. It's right down here. You guys are up there. Blacksburg is over here. I was asking Mr. Google for something yesterday, and this popped up, and I was like, really? I have never been to Ceres, Virginia. I may have to go and check it out, but I have a feeling from what I can tell that there's not much more than a post office there. So there may not be a whole lot to see. But Ceres is named after a Roman god of agriculture. That's sort of an agricultural, it's also a mining region, but I assume that it's agriculture that got its name. It's the largest body in the asteroid belt, and a lot of people, you talk to people and they know what Mars is, they know what Mercury is, but they don't know Ceres, what's that? And it's wading into the territory of calling it a dwarf planet sort of, riles certain passions or upsets or whatever else. But it's large enough to be round, which from my point of view is a very interesting aspect of Ceres, although it's not actually completely round, and we'll talk more about that. But this is the orbit of Ceres. Here's Earth, here's Mars, here's Jupiter. So it's in the outer part of the asteroid belt. And just to give you a sense of how much it's weighted, if this is like university administration kind of graphics and pie charts. This is the mass of Ceres, if this is the entire mass of the asteroid belt. So Ceres is the biggest by far. Vesta is next, Pallas, and then you get into some things that I can't even keep straight in memory. There will be a mission to Psyche in a few years, and that's supposed to be a metallic asteroid, which should be a very interesting find. But Ceres is by far the largest. If we look at this in another type of measure, this is the diameter of the body in log scale, 1, 10, 100. This is the number of asteroids, 10,000. I think this must have been made for somebody who thought whoever was the intended audience wouldn't like scientific notation, but 10 million, 100 million. So you can see there's this precipitous fall off. There's Ceres, there's the next largest things, and you get down to much smaller size, and there's a great number of them, and it falls off on something like a log scale like this. And this will return when we talk about craters in a little bit. So this is what you could see from a telescope, from Hubble. This was our best view of Ceres before the Dawn mission. And I've seen this figure a lot of times, and I hadn't really thought about it until I was putting this talk together. But, Ceres' surface, and in fact you read old papers and they say that the surface of Ceres is very dark. I always envisioned from seeing this picture that Ceres was going to be this bright white ball of ice, right? And it really isn't. We're going to sort of, my tour on that was, okay, this is what we see, and I was sitting here thinking about what could Ceres be like and so forth, and this is sort of the picture I had in my mind. And I got that picture because we knew that the surface was volatile or water-rich. We knew that there's an average surface temperature of something like 150 K. And so at that temperature, ice should not be able to retain craters for more than 5 or 10 million years or something like that. The craters should all have relaxed away. And I thought we would get to Ceres, and this is sort of what we would see. Of course, that's actually Enceladus, if you know anything like that, but I had to sort of pick something that was what was in my mind. We got to Ceres, and this is what we saw. So right away, it was clear to me that my initial ideas about Ceres couldn't possibly be right. All right? I don't know what was going on, but clearly it's not right. This is from the sort of the survey orbit, or the largest orbit that they did, and sort of the first images that were coming through. And those of you who remember when Ceres was coming through, there's these bright spots in Orbital Crater that people were like, are these aliens, or what is going on, why is this light shining at us, and so forth. And I'm mostly talking about the interior, but I'll put a few slides in here because I figured you'd want to talk about them or know about them. So the things that I look at to constrain interiors of bodies, and I'm very much interested in, how bodies got from how they initially, came together in the solar nebula to how we see them today. And so we need to know the mass and the volume, and we knew that pretty well before the mission even, at least well enough to get a good start on things. We need to, the surface composition is helpful, but the surface and the interior may not be directly related. The crater distribution and the shape of the craters, or the crater morphology, is going to be very useful for me, as well as the global shape of the body. It's not completely round. It rotates every 9 hours, so it's kind of a fast rotating body, and it's a lot like me. The middle is a little bit bigger than it should be, and it's under tall for how it is. And then we also have laboratory measurements of the materials that we think are there, and that can enter into the modeling that we're doing. So, a mean density of 2.1 or 2162 kilograms per meter cubed. To me, this is interesting because, if you think about planets, they're made up of ice, rock, and iron, and those are kind of your building blocks. And so right away you can tell that there's got to be a lot of volatile stuff in Ceres to get a density that's this low. Density of the moon is about 3,400, and that's mostly rock with a tiny, tiny little bit of core. And so right away we know that we're in a regime that's actually kind of uncomfortable for me, because I've dealt with Mercury and Venus and Mars, and I'm used to these rocks, and I've had to learn all of these mineral properties and strengths and stuff like that, and suddenly everything in Ceres is different that we're dealing with. So some of the pieces of the surface composition, Dawn had spectral instruments, ammonia-bearing hydrated minerals, as you can see there, that came from the Veer instruments. That mineralogy, and in fact this sort of particular breakdown, is really consistent with the geophysical methods, as well as these other methodologies. There's still some debate about all of these pieces, but this one turned out to be to me, a very surprising material. If you study the Earth and you're interested in hydrocarbons, there are these methane clathrates on the ocean floor that sequester a lot of methane and carbon resources. They're basically an ice that can exist at the continental shelf, slightly buried pressures and temperatures. It's not something that I would necessarily have thought of as being a part of a planetary body, but we'll see where that becomes important. And as well as there's sort of this range of rock and salts, and Julie calls these hydrated salts. I've never thought of a carbonate as a salt, but that is the picture. So we'll talk about how to resolve that and how to deal with that. So anyone, if you know anything about Ceres, you probably say, what are the bright spots, right? And I'm an interior guy, not a surface guy, so I'm not the best person to tell you firsthand, but these spots are in this crater called Orbital Crater, and I must have been asleep in the team meeting where they came up with the name, because I was like, I wonder what Orbital is. And it turns out Orbital was an assistant to the god of Ceres, and I never would have thought that gods had assistants, but sort of like deans, I suppose, or something. But so Orbital Crater is where these bright spots are, and here in this particular image you can see that there's a bright spot toward the center, and there's another kind of group of spots toward the east a little bit. We zoom in a little bit more. Orbital Craters about 92 kilometers across. It's a fresh, relatively young crater. I can probably get away with it here because there aren't the crater counting people here to argue about the age of the crater, but it's certainly less than 30 million years. I've seen some papers saying it's less than 10 million years, so it's very young. And these spots called faculae are also, and as you can see as we zoom in, there's more distinct structure to these spots than you saw in the original image. And as, in fact, the extended mission of Dawn sort of flew right over the top of the crater in order to get as much information as they could. You can see that compared to the dark floor, it's something like 10 times as bright or something like that. And the spectral characteristics are interpreted to be carbonate, and they actually, in this paper, Marie de Sanctis suggested that this is actually, outside of Earth, the most abundant carbonates that we know of in the solar system, which I thought was kind of interesting, because on Earth, carbonates are all due to critters, pretty much. But I don't think these are critter related. I'm not going to suggest that.
What are the false colors there representing? What are the colors in the false color image they're representing?
What are the colors representing?
Yeah, like in the image,
Yeah.
the yellow and blue.
You know, that's a really good question. I'm not that much of a interpreter on that. Do you know what?
I think it's two kinds of carbonates here.
Okay.
But don't pin me down on which one is which.
Mm-hmm. And this is the most recent image, basically taking the stereo topography and wrapping this stuff in it. And interesting to me, there's still a debate to a certain extent of how much of this is related to impact volcanism or whether this is all hydrothermal post-dating the impact volcanism. But you can sort of see that there's stuff that's at higher elevations, and it's not obvious that it like came out of a cone and all flowed down. The interrelationships are really complicated, and it's, you know, the amazing thing is this is higher resolution than we've had on, you know, any of the Galilean satellites or any of the Saturnian satellites. So this is the highest resolution view we've gotten of something from an ice surface covered body, and it's sort of intriguing because all of the emphasis has been on, you know, Enceladus and the Saturnian moons, so forth. And it's kind of interesting to think about how much of what we're seeing here, you know, might we see a whole lot more rich things going on some of these icy moons if we can ever get a mission to look at one of them as closely as we're looking at Dawn is looking at Ceres, or has looked at Ceres. So, you know, it's a intrusive. I think everyone agrees with that. It didn't come from above somehow. Somebody once suggested that it looked like if someone dropped a sack of flour from great height or something like that, but that's what happens when you crowdsource science. I think that was sent into one of the websites or something. So, Orbital's faculae, these bright spots, are unique in that other craters from Ceres don't see this. Orbital is the only one that sees this. And while Ceres is certainly billions of years old, 4 billion years old or something like that, Occupies crater and the facula are less than 10 million years old. And that's interesting because as small as Ceres is, and unlike the other icy moons that have tidal heating sources, it's surprising that Ceres has had this much internal stuff going on. And the question of how you keep a brine in Ceres, or whether you need to keep, whether you could just do this with impact heating or not, I'm not entirely sure that that's ruled out. But where this heat is coming from on this small body that should have cooled and you wouldn't have thought would be as geologically active as it is sort of an interesting question. These faculae have a very strong compositional analog to the lone agreed upon cryovolcanic structure. I think there's some other domes that may be other volcanic structures, but Ahuna Mons is the one sort of, they call it Lonely Mountain. I didn't look up what Ahuna Mons means, but I don't think it really means Lonely Mountain. So it's, there's a compositional analog here, which is very interesting because Ahuna Mons is a elevated volcanic-like structure. I already said it's supposed to be the largest deposit of carbonates, I would say, that we know of, because there could well be some carbonates buried, like maybe on Mars or something like that we don't know about. And this large plateau, Haname Plateau, which we'll talk about more, happens to be where Occupies crater is located, and it has a somewhat unique subsurface structure compared to other parts of Ceres. And I'll touch on that a little bit. I sort of paraphrased from this paper to simplify it now, and I hope I didn't paraphrase it too much. But I want to look at the crater distribution, because this was really interesting to me, and this is a paper by a number of people from the team. This is Ceres topography, and the largest craters, and I forget whether they're greater than 100 kilometers in diameter or exactly what the cutoff was. The largest craters are outlined in yellow. You know, there are some smaller craters in here that you can see, but this is the group of largest identified craters. This is a realization taking the structure of the asteroid belt and assuming that that structure has been the same in terms of the distribution of objects, and that those objects would have hit Ceres at some random time throughout the evolution of the solar system. Time is given here in color. You can see most of these things happen early on, but even if you look at the blue, which are the things that happened in the last billion years, there's far less identified craters in Ceres than what you would expect. And this is a log plot that shows you the same thing. The dashed line is this main belt asteroid model for the anticipated size of craters that would be created on Ceres over a 4.5 billion year lifetime versus their cumulative number per area. So, you know, this is the main belt model, which is very close to a straight line here. The blue are the realization of data from Vesta, which is hard to distinguish from this line. And Ceres is, you know, what you see here visually very clearly is devoid of large impacts. And so this is something that I think we need to really take into account in understanding what's going on in Ceres. There's also crater morphology, in other words, how much the shape of the craters has evolved over time. And this is sort of a cartoon of what one might expect to happen, that after an impact crater you get an upwelling of material under here due to the heat and the energy that's deposited during the impactor. And with time, this topography of the crater and this topography on the boundary between whatever the crustal material is and whatever the material underneath is begins to relax. And this is a very well-known geophysical student problem. You can relate this to the evolution of ice sheets on Earth and the rebound of ice after the last ice age. And your relaxation time depends on the viscosity of the material divided by the density and gravity. And this is essentially why at the very beginning I said these craters ought to relax very quickly on Ceres, because if you thought the surface is dominantly ice, then this relaxation time is something like 10 to 15 million years. And this is an E-fold sort of time. So one every E, topography relaxes by a factor of E for every time period of this case. And this is another paper by the Dawn team. There's a latitude dependence here because the solar insolation is affecting Ceres. The low latitudes are warmer than the higher latitudes due to the angle that the sun is hitting the surface and the surface area that's being hit per unit area. Apparent depth of the crater, which is essentially the depth of the crater relative to an estimate of the depth of the rim. The different craters are categorized here by size. So this little dot is 100 kilometers. So these are actually 200 plus kilometer craters. These are about 100, so forth. All of these craters here are outside of this envelope, and this envelope is based on pure ice where the different curves are dependent on whether the grain size of the ice that you're talking about, because these mechanisms are dependent on the grain size of the ice, and until we have samples, that's not something we have direct access to. But what you can see is they all predict essentially there should be no craters at low latitudes, sort of like my initial picture. And that's certainly not the case in what we see. So this material has to be a lot stronger than pure water ice. And exactly what it is still a matter of some debate. But that's partly where the clathrates come in, and I'll show you that in a couple of slides. This is also in this same paper, and I just show you that the story is more complex than you would think. And in one of Hannah's more recent papers, she pointed this out as well. Here are two craters of almost identical size, right? And both of them have other smaller craters in them, so they're both old. They've been, had other craters in them beforehand. This one has almost completely, this line here represents this topographic profile here, 400 kilometers across here, 6 to minus 6 kilometers here. You can see that you still see a little bit of the rims of these craters, but the floor of the crater has basically rebounded and is almost at the same elevation as the surrounding material, right? Whereas this crater over here has, a significant topography left in it. And so lateral variations in the crustal properties are probably important. I mean, it's hard to believe that that's not the case, because both of these look to be at least a certain amount of similar in age, they're similar in size. And then, of course, there's this one crater, Kirwan, here, which you can hardly see the outer rim of this crater anymore, but there's this very deep central part of the crater. And there's nothing like this in the solar system that we've ever seen before. So it's a truly unique situation going on there. So the morphology tells us it's got to be a lot stronger than pure water ice, but that doesn't help us out too much. So this is laboratory data, and I just picked out 3 materials. There's water ice. Here's clathrate, and we like clathrate because it's very low density. It's not much more dense than water ice, so it helps us bring that density down. But it's several orders of magnitude stronger than water ice. Okay, and this, viscosities, for those of you who don't live in the world of viscous deformation, which astronomers, why would you? But the viscosity of rock underneath us here in the deeper part of the Earth is probably somewhere around 10 to the 21. Right? Serpentine is a favorite rock of mine. It's very important in subduction zones on Earth. It's basically rock that has water bound to the mineral structurally. So it's not in the material mechanically, but it's physically bound to the mineral structure of this. And it's weak, and it's weak relative to other things that are shallow in the mantle, and it's low density, and it's actually one of the few things that's been measured at really low temperatures, so it's a good analog for me to work with to basically say hydrated rock. You can see that it's very strong, and it doesn't depend very much on temperature, whereas ice becomes exponentially weaker the closer you get to the melting point of ice. Clathrate gets there. But these are surface temperature ranges here in dark color. And the way I like to keep things simple, because I'm a simple kind of guy, and there's very few times a geophysicist can cite Einstein. And so it's kind of fun. I mean, a little different from you guys. But there's this relationship by Einstein, sometimes goes by Einstein-Rocco, where they were looking at a fluid with rigid spheres. And so I'm thinking about the fluid as being ice, and the rigid spheres as being rock, because they're not completely rigid, but they're many orders of magnitude higher in viscosity. And what happens if you do that is this is the fraction of rock. So if you get more than about 30% or 35, maybe even 40% of ice in this system, the viscosity essentially goes down and becomes almost like ice. It's like the rock isn't there, or the spheres aren't there. And so, using that simple relationship, we basically concluded that you can't have more than 30-35% ice in this surface material. It's got to be something else. where that something else is, whatever it is stronger. If you make that 30 or 40, if you make that 60% of stuff be rock, then your crust is too dense. And that's why we like clathrate, because clathrate is strong, but it's also low density. So it's a way that we can get the density in that crustal layer and the stiffness of that layer both to work out. So now we turn to flattening and gravity. And I said Ceres is not quite a sphere. It's due to hydrostatic equilibrium. If it was in hydrostatic equilibrium, the rotation, it should bulge, and its polar radii should be much smaller than the equatorial radii. And actually, this is the measurements from the Dawn mission, and there's something called the flattening, traditional geophysical measurement, which is basically just the ratio of those two radii divided by the equatorial radii. Ceres is a little bit more complicated, and all planets are, but Ceres is a little bit more complicated. If it were really in hydrostatic equilibrium, then the b-axis, which would be the equatorial axis coming out of the page, because it's a 3D object, the b-axis and the a-axis should be the same. And they're not. They're off by about 2 kilometers, which for me wasn't a very big deal, but gravity people worry about things at the levels that 2 kilometers is a big deal to them. But what I'm going to actually use instead of the flattening is the gravitational equivalent. So U is a gravitational potential, S is this surface, and I am assuming that this surface is basically an ellipsoid, so I'm assuming that there is no theta dependence. So these potential can be related to a Legendre polynomial and this coefficient that for historical reasons is called J2, right? But all it really is the gravity equivalent of the shape flattening. And it's scaled in this way because gravity people like Legendre polynomials and so forth, and it all falls out of the math nicely, but we don't need to worry about that. The gravity mission, the gravity team has measured J2 very accurately, and you can solve a set of equations, which we don't need to get into, in order to match J2 and tell you about the internal structure. And this is the world I live in. We think about a possible core, a mantle, and a crust. Those could each have a different density. And then we don't know the radius of this boundary between the mantle and the core. We don't know the radius of the boundary between this crust and this mantle material. So we have 5 unknowns. And we have 2 constraints. All right? Most people would be appalled by this, but this is the world of geophysics, and we guess to and solve and hope that we're close, or something like that. So I did some sort of a hybrid of a Monte Carlo approach. I tried using Markov chain Monte Carlo because if you say Markov chain Monte Carlo, everybody nods approvingly, even though nobody really understands what you're doing. But I used something ridiculous like 1 billion models, but solving these equations is really quick, so I could do this on a weekend in my laptop. My tech people were appalled that I was actually running something like that on a laptop. It's not made to do that. Well, And this is what sort of came out. Top panel, so we're looking at histograms. Top panel is the density of the crust, and I get anywhere from about 1,300. I stopped here at 1,450. My modeling would keep going and allow the density of the crust to be even more dense. Other team members took a different approach, used a different data set, and they constrained this further, and so I put a constraint in to not let mine go much higher. You can see, actually, I was kind of happy with this because it looks vaguely Gaussian, and there was a Gaussian input, so it was kind of nice to see a Gaussian output for the mantle. It's a little bit lower in density than what you would want for certain meteorites, or have about 2,500 kilograms per meter cube. So, but it's almost like a carbonaceous chondrite, not quite. And this was the density of a core, and you can see I have virtually no constraint on it. The model's actually almost, in terms of frequency, they kind of said if there is a core, it's not much more dense because this is 25. So probably the most likely models actually had the mantle and the core being the same thing, or essentially there is no core. Had this sort of a constraint on, so this is the radius is 470, so 20, 30, 35 to 40 kilometer thick crust. And the models really wanted to keep pushing that to be even thinner in what I was doing, which again was not what other team members were getting, and so we I sort of compromised in keeping this like that. So if there is a core, it's small and it's not much more dense than the mantle, but we can't rule it out. Now, why did I care? Why am I making a big deal out of a core? Well, people talk about Ceres as an analog for the early protoplanetesimals. And there's a big question as to whether differentiation happens after planets aggregate, or if they differentiate and then aggregate together and differentiate and aggregate together and so forth. And so, all planets, I'm not sure why they put a question mark after the core, because we know the moon has a core, but all planets have cores. The question is, do these building blocks already have a core, or does the core not ever form until afterwards, right? And so what it means all comes down to the major heater that would be going on early in the solar system, aluminum-26, which decays on a 700,000 year time scale or something like that. So 700 million or 7 million years or 10 half-lives after the last event that created aluminum-26, the last supernova or whatever that aluminum-26 was created. 7 million years later, the aluminum-26 is pretty much all gone, right? So the earliest things we've dated in the solar system are these calcium-aluminum inclusions inside chondritic meteorites. Okay, this one is Allende, the meteorite that fell. It had the good fortune to fall in Mexico, like right when NASA was funding all the labs to study moon rocks. And so this is like incredibly studied because they all had these labs and they were anxiously waiting for the moon rocks to come back. So now they had a meteorite that was a fall and that hadn't been pristinely. So Allende is really important in the lore of meteorites. And there are these little round things called chondrules, and people debate endlessly about how chondrules formed, but essentially this meteorite is an aggregate of all these chondrules with these little fluffy pieces of calcium aluminum, and these calcium aluminum inclusions are the oldest things that we have dates on. And so this becomes sort of the marker for the early part of the solar system. So however many million years after the calcium, I think this is amazing. Like, these things presumably formed out of high temperature condensates. Within 5 million years, you have planets, or something the size of Ceres. You have to form that pretty quick. Anyway, a diversion. Crustal density, crustal thickness. 3 different studies, all people from the Dawn team. Anton Ermakov here, Gespi Mitri, and another team here have a very different set of error bounds. And then my investigation here, I put the arrows here because my modeling would want to push these things further, and I sort of truncated them to what Anton had discovered. You can see that we all have some overlap, but given the errors, we're all a little bit different. But we have an idea that the crust is 12 to 13.5 100 kilograms per meter cubed, and that the crust is 35 to 45 kilometers thick. All right, the differences come down to really technical stuff, and you don't want to get into the difference. I really only use the shape and the gravity. Anton and Mitri use very high order aspects of the gravitational field, but they assumed that everything is behaving with isostasy. I'm a little bit nervous about that because of the 2 craters I showed you that looked so different. That's telling us that the crust isn't, isostasy would assume that anywhere you go on the surface you have the same crust for all practical purposes, and that it's uniform. And we kind of know that isn't really right. And so I'm a little nervous about what that difference is still telling us. But that's nothing compared to the problems of rheology. Right? So in a paper by another group of team members that I worked on, plausible compositions and evolutionary histories of Ceres could result in strong, weak, or heterogeneous rheology for the interior part of Ceres. In other words, it can be whatever you want. And instead of taking craters, they took the topography of Ceres, and they noticed that Ceres topography didn't fall on the trend that they expected, and it didn't fall on the trend that Vesta had, and that this anomalous, essentially relaxed topography was being caused by, deformation, and they could then determine the rheology of the material. Well, they used a 2-layer model. They said that the outer part of this is weak and it varies exponentially and in a very interesting way, and that the lower part is stiff. And here's their residual square of their residuals. Below about 100 kilometers, it didn't make a difference where they put this rheology. So basically, from a modeler, this is great. You have unconstrained parameter space, right? Constraint-free modeling. On the other hand, it's really a pain because you can get whatever answer you want. This is what intrigues me about this. This is the density difference that came from the first modeling study I showed you. This is the change in rheology from really, really strong at the surface, so that you have these craters, to really, really weak at 100 kilometers depth, exponentially decaying. This stuff is supposed to be rock. Rock at 100 degrees C, 100 degrees K, or 200 degrees K, should be way up here. So what is this telling us? Why is this upper part of this high density stuff so much weaker than what your models would predict? This is rock, right? This is a pretty good analog for what we're supposed to have, and its viscosities here in the 10 to the 23, 10 to the 24 range, and this is 10 to the 19. 4 orders of magnitude. Even for rheology, that's a lot, you know. So what we know is that just saying this is ice, salt, clathrate, rock over hydrated mantle has to be too simplistic. And so I wanted to do, I'm going to show you a couple of one model, and then we'll call it quits because you endured enough of this. So if we assume that heat is leaving Ceres only by conduction, there's a number of reasons why I think we can rule out that particular model. Among other things, it's not going to be consistent with that really weak rheology constraint. If we assume that the outer shell is still weaker than rock, and it convects, and that the interior is really rigid, we have a problem because that convecting ice in the exterior should wipe out all the surface features that we see, and we would see even less craters than we would think. Then this is what I'm going to look at, this case over here, or we could have even a lower viscosity than this here, but I'm not going to be looking at that particular case right now. So, what goes into the model? Who wants equations when you can have haiku, right? So those are the equations for incompressible convection in a viscous material, incompressible, momentum conservation, energy balance. You know, very zen. So that's what goes into this, into a 3D sphere. We have the heat source. Now we're worrying about the long-lived radioactive elements. And unlike the world I came from, where planets start hot because you're bringing all this material together from a very far distance, and as it collides and comes together, that gravitational potential energy turns into thermal energy. Right? That should raise the temperature of a planet like Earth thousands of degrees. For Ceres, it raises it like 50 degrees or something like that. It's amazing how little that affects. So unlike the world I'm used to, where planets start out hot and they cool, Ceres heats up and then cools. And it does it in a very interesting way. So I'm going to look at one particular set of models. They do have they're going to have a little bit weaker interior than I show you on this particular figure, but I'll just show you the movie. Very beginning of time, the weak, icy material deforms. You're looking at contours of temperature, and this big surface is an isosurface of temperature. This is scaled model time. You get this ginormous instability where the stuff that's in the interior, which is hotter and begins to heat up with time but can't move because it's more viscous, essentially undergoes an instability, goes off to one side, and after this, what happens because of that decaying heating, there's not enough heat for this cycle to happen again. So basically you get something that just goes on, and in the interest of time we'll push ahead. If you look at the average temperature as a function of time, it does something like this. You get this one unique instability. I could spend a lot of time saying, why does this happen? It happens right where math says it should happen. There's the fundamental critical Rayleigh number in a sphere is worked out by Chandrasekhar, and it should happen with the blue line here. This is heating at the early solar system. This is heating at present day. So these are the two parts of the Rayleigh number I don't know: how much heat there is and what the rheology is. And these are the critical Rayleigh numbers. The difference is whether it's a free slip surface or a no slip surface. But this instability, the first instability that should happen is this degree 1, this one hemisphere pushing off into the other. And it happens exactly where theory says it should happen, which really nice when that actually does happen from a modeler. So the observations, I think this explains. There's one topographic high on Ceres. This is a model of topography, 45 kilometers versus 35. No, this must be crustal thickness model. Sorry, it is crustal thickness model. One region of thickened crust, Hanami Planum. The stars indicate where there's a whole bunch of domes. I'm not going to try and explain the domes. There's a whole bunch of features here that have been interpreted to be extensional faults. And if you imagine that that hot material comes up from below, and as it's coming up, the hydrated part of it dehydrates, so the rock becomes less water-rich, and that water underplates the crust, you would get a region of thickened crust. And you would also get, so my interpretation is this giant plume could have come up in this region. I'm not going to spend a lot of time on this, but this is stresses from the model, the stresses from the model that are created by this thing pushing up underneath the lithosphere would create extensional stresses that are kind of in the right pattern for this observed stresses. During this event, you would get a big spike in surface mobility. So essentially when that stuff comes up, it would strain the entire surface. And it would strain it by, in fact, the strains are, that's bad. The strains are of order 1. And that means any crater that would have been there would be strained to the point you wouldn't see the crater anymore. So that early phase of stuff that came up, 1 billion years, would reset the surface, and it would explain where those old craters went. It would explain that region of thickened topography. And there's one other thing it should be explaining too, and now I don't know why Microsoft failed me. But that's basically the picture I have. I sort of thought about it as Ceres as one and done, you know, because you get this one pulse of plume material coming up, it resets the surface, it creates this thick crust, it creates these fracture structures, and after that there isn't enough heat left in the interior for anything else to continue on like this. So this sort of the model, I think that it explains a number of the observations on Ceres. I'm out of time, so I think I have a student who's played a little bit with the topography and tried to see if we can tell this story consistently looking at another set of data. But I won't try and thrust that on you because it's already 4 o'clock and you've been very patient. So thank you very much.
Do 2 questions, and then there are time slots that he has this afternoon and tomorrow morning if you'd like to chat more with him. Any questions?
I'm going to talk with you after this, I think, but I'll ask one while we're here. So I'm curious, there must be some asymmetry that causes this hemispherical plume, right? So does that come from rotation or something else? In the models, is that something you put in, or is that something that arises?
There is nothing in the model that I put in that is particularly driving the model to come up one place or another. In fact, the plume, I have no control in the model of where the plume would come up. It's basically, in terms of the model, it's hard for me to believe that it's the initial conditions I put in 1 billion years later affecting this. It's most likely random numerical noise that creates enough of an instability that grows. I actually have, let's find it. I don't know if you can see this or not, if it shows up, but I looked at the temperature power spectrum as a function of time, and what you can see, L equals 0 is the constant mode, and there's no change in the mean temperature here. But the L equals 1 mode is red, and it just grows with time and grows faster than anything else. And it starts down here after 250 million years. So it's just the model itself in self-organizing, reaches this point. And it's sort of interesting because the fundamental modes of the sphere, degree 1 is the most unstable mode. And so the numerical model is just actually, it's a little surprising to some of my friends who saw this, that the numerical model was actually picking that out. I don't know that I have a better explanation than that.
Any other questions?
So if we were to have a billionaire want to mine resources off of Ceres, what is there that is of any substantial value? Can you, for example, really get a lot of water out of Ceres and use it as a reservoir for explorations?
Can I answer this? Unless you have something to... So, ice is the thing you want from Ceres to make hydrazine. Rocket fuel.
Mm-hmm. I mean, the clathrate is basically methane hydrate. And so, I mean, people are talking about mining this off of the seafloor, for hydrocarbon resources or something like that, and then there's other people who are horrified at the thought of putting more hydrocarbons into the atmosphere. But, for rocket fuel or potential, hydrogen or methane are probably the most useful things you could get off Ceres. Psyche, the metallic asteroid, there's a bunch of people who think that, there's $1 trillion worth of platinum on Psyche or something like that. And, there probably is if you could grind it all up and extract it all or something like that. But I don't know. But that's what I would look at. Anything else? No? Well, thank you very much for your attention.